Why did we call it rho prime? Does anybody know, other than Will? Can anybody guess? Has anybody heard of the phase shift parameter, rho? So, since at least Van de Hulse, people have used the phase shift parameter like that. And it does a very good job of unifying scattering descriptions. But we found that rho prime does better. And we proved it. So let's take a look at rho prime in action. This is just for forward scattering. We've got rho prime, we've got forward scattering divided by the Rayleigh cross-section, by the Rayleigh scattering, versus this internal coupling parameter, rho prime. When it's small, the scattering is identically equal to Rayleigh scattering. As rho prime goes through 1, some oscillations occur, as big as a factor of 3. And then a negative rho prime, an inverse square rho prime functionality develops. Now let me stress that this is for refractive indices ranging from 1.01 to 2, different colors. By holding the refractive index constant to change rho prime, we had to change the size parameter, widely varied. So the point is, all these refractive indices and all these different sizes collapse to the same curve. To emphasize this functionality, we took the same parameter here and multiplied by rho prime squared. So now this shoots up and this levels off at 1. We did this with rho as well. Rho works, but it misses down here. These scatter around by about a factor of 3. So it doesn't do as good of a job. And it's not surprising that rho does a half-assed job, excuse my language, because of course this is very closely similar to this equation here. So rho prime provides this universal description. Now what I intend to do is I'm going to give you one more slide, and then Friday, tomorrow, I'm going to come back to these 2 slides and repeat myself. All right? So that it can soak in your head for a while, and then we'll talk about it again, and then we'll have some discussion, or we can have discussion today, of course, too. So let me do one more slide, and instead of the forward scattering, this is the whole phase function. Now, it's full of detail. Here is the scattered intensity as a function of angle, right? Divided by the Rayleigh scattering. Here's the diffraction limit, the dashed line. Here are different rho prime values. But these rho prime values have 3 different refractive indices. So of course, what we're doing is changing the size as well. But the point is that if rho prime is the same, regardless of the refractive index, the curves fall together. You're right, not perfectly. So the gap, what would that be? Maybe a factor of 2. Seems to get better at large rho prime. Okay. Here's some dispersion as well. But still, quite a bit of unification that we never had before. When rho prime is small, we just have this little tail coming off, and there's the enhanced backscatter. But notice it touches base. Touches base with the diffraction limit. Getting bigger and bigger, and this equal tangent -2 between the guniae and the hump. starts to appear. By the time we're at 30, ever so slightly, the minus 3 starts to appear. And of course, by the time we're up to 1,000, minus 3 is well displayed. The equal tangent of minus 2 that we don't understand, I keep telling you that, occurs. The hump is there. Okay. The hump position, and of course we coined the term for obvious reasons, the hump position seems to be centered at rho prime, interestingly enough. Not entirely sure why. So I could point out that whereas we first plotted things like this 16 years ago and published it, it sort of sat in iniquity for a while. And then in the last 2 or 3 years, we got all these results. So a lot of the things that we're saying, we're not entirely sure. But, so this shows the universality with rho prime. This fall off, of course, is the fact that I showed in the previous slide that the intensity is decreasing with rho prime, away from the Rayleigh scatter. Finally, let me just give you a thought. How might we explain this pattern? Maybe it's 2 diffraction patterns stacked on top of each other. There's diffraction from the overall particle, right, with size r, but it's now a 2-dimensional object because it's so refractive and thick. And then there's, notice, because this is touching base with the original and kind of has a minus 4, although it's a little bigger, maybe there's underneath this 3-dimensional diffraction at larger QR, which means smaller size. So maybe we've got a spherical particle, and the whole particle itself is causing the 2-dimensional diffraction. And inside of it, there's a smaller particle that has a vestige of 3-dimensional diffraction. And I think some of you might know that in large spheres, there's a hot spot back there. Maybe it's a hot spot. I don't know. But that's where we are right now. We're trying to figure that out. So there, I took 60-some minutes, which is a little too long. Let me stop and see if there's any discussion. It occurs to me, since Apurva is helping with this, why don't I send you my slides and you send it to the group? Yeah. Okay? And then tomorrow, our last day, you guys will be loaded, right, if you want to be, to ask me a zillion questions. Now, I've got a lot of lecture after this. I've got another 50 minutes, I think, because we're going to get into non-spherical particles, dust grains, fractals. It all comes together, though, with Q-space analysis. But at least if I prep you, then we'll really interact well. Okay? Okay. But even with that pending, if you want to talk about anything right now, I'm open.
I don't know whether it's because I missed yesterday's lecture about the Q-space. So we use forward transform to transfer from X-space to Q-space, right? Just to
Forward scatter.
Fourier transform.
Oh, Fourier transform. Yes.
To the Q-space.
Yeah.
And I kind of lose the control why we want to solve it on Q-space rather than on the original dimension.
Okay, well, the light forces us, you might say, to go into Q-space. Because when we set up diffraction, we realized that to take care of the waves, a Fourier transform naturally appears. Maybe what I could do, that's a good question. Is Sorensen trying to make you do Q space, or is nature trying to make you do Q space? So this makes us do Q space for diffraction. So the very fact that I've erased it now, let's remember lecture number 1. Number 1 said, okay, you can represent a wave in space as a sine wave, but I pointed out that if we use this formulation, it's easier to deal with mathematically. And notice that's already starting to look like part of a Fourier transform. Okay? And then, with this diagram, we found that when light went up to the detector, we had the field at the detector from just one of these, one point scatterer, was proportional to e to the I q dot r, point scatter at r. And then we had to add up all these. They were at different r's. Can you see it coming? So I'm going to add all these up. E total at detector is to add all these up over the volume of the particle. Or just put in the density function of the particle and integrate all over space, and this will tell you where the particle is. And there it is. It's a Fourier transform. So don't blame me. Blame Mother Nature. Other questions?
So in the last slide, we see there are two relatively flat regime, and then we see three-dimensional diffraction, and then the two-dimensional diffraction, and then three-dimensional.
Yeah, that's my proposition,
Okay.
my hypothesis.
So in this figure, can we see whether the length scale where we start to see the three-dimensional diffraction is related to the length scale at which we start to see the two-dimensional diffraction?
So I caught the first part of that. So you're asking about the length scale of the three-dimensional diffraction,
Right.
which looks like in this case 1,000 times smaller than the length scale of the particle, right? And you want to compare that to what?
When we compare to all of this curve over here, is there any connection between these two length scale where we start to see the 3D and 2D diffraction?
Yeah. I still don't understand that connection to the other.
So he's saying that the length scale at which the 2D diffraction kicks in, are these correlated, the 2D and the 3D for different?
Yeah.
Will you get the tangent line connecting too?
Yeah, well, the length scale, this length scale, notice, holds the whole time. So even when it's a weakly refractive object and it's ready to buy gons, we're going to see the size of the sphere. Let's remember that if QR equals to 1, sucker got stuck. So when QR equals 1, Q is at 1 over R, or you could say Q to the minus 1 equals R, right? All three of those. So we've managed to detect the size of the particle. the maybe we're referring to the fact that right around 30, rho prime of 30, we'd start to see ever so slightly the two-dimensional regime. And then we're starting to get a hump as well. Notice for 3, there's no hump. For 10, there's no hump. It's only when this starts to cave in, dropping away from the -2 line. Notice the -2 line almost works up here, but it definitely does not work here. You know, as I said, I proposed these points of view. It's good to have hypotheses and to test them. And we've looked at it. It doesn't quite work. So it's perplexing to me. I don't know the answer.
Okay, so actually I'm just thinking if we have an object and inside we have this hotspot, maybe twice the size of the whole object, how is the size of the hotspot going to change, maybe twice the whole object?
So if I make the whole object twice as big.
Right.
So if you have the same index, then you have bigger rho prime, and then that tangent line would still be there. So that crossover in the hump would be at larger QR. So then you relate that to a smaller size, and you can kind of see that when you get a larger lens, focusing that light on a more intense, smaller spot.
Yeah, I agree. So that's worth thinking about. So if we do double the size and keep the index fraction the same, this will go to 2,000. And it'll stay here. This will go to 2,000. So it will come out a factor of 2. There's twice as big. So,
So you just
The
have another.
hotspot just scales up.
Yeah, you just have the same gravity. It's just like
Yeah.
between 100 and 1,000, right? So the hump would just move over down that -4 exponent.
yeah, it'll slip along here. And this will lower a little more, as we can see in the other ones. And then the relative to R, right, relative to the new R, this will be smaller yet. So we double the size.
If you double size, then it moves down double QR, right?
Yeah, maybe one way to do this is to remove the R. Let's try this. Let's just plot this versus Q. So here we go. We got the -3, the hump, and the -4. And if this is versus Q, then this point right here is R to the -1. And since this is where QR equals rho prime, this is where Q equals rho prime over R. Rho prime over R. So if R gets bigger, the rho prime is 2kr index refraction stuff, right? Over R. The R's cancel. So it stays at the same place. Yeah, so the length scale, so I got to invert this to get a length scale. So let's see, let's call it the size of whatever this is. Will be something like lambda over 4 pi, and then the index refraction functionality. So it stays constant. So I would conclude that if we double the size, the spot stays the same size, or whatever's causing that thing.
Maybe to understand this, why are we talking about hotspot? Like, why are we?
Okay. And we have to be careful with that. So, first of all, let me just describe what a hotspot is, and I can go to the optics limit. So we have a big particle, and light comes in and refracts. Right? A lot of light will come back here and tend to focus, and we get this hot spot. And even if you do the Mie calculations for the internal field, one finds it's very complex. You can imagine a topographical map, but indeed, you often find a lot of intensity back here.
But it's only one.
It's only one, but it's a mess, okay? And it can have structure. I drew a nice circular spot here, but it can have structure. So that's what's so difficult about trying to figure out what this hump is due to. But regardless, maybe even if we don't call it a hot spot, the inflection implies a size. And so whatever it is that's causing this, Pi's question points out that if we double the radius of the particle, this will adjust such that whatever that thing is, it's the same size. So here's the answer, I think, to Pi's question in schematic form. Right, twice as big, same size.
So, could it be that it's not a hotspot, but just some structure of the inside of the particle, the big particle, that you're now starting to see the finer details of the inside of the particle?
No. Remember, we're assuming uniform particles. This has got nothing to do with the particle inhomogeneities. This is a homogeneous particle. It's a ball of glass. It's a drop of water. Right? But we can change its size. So I think that's an interesting question, and I think that's an interesting result. Maybe, I mean, if we now go this way, I cheated a little bit. I made this bigger than that. But I'm trying to now shrink it. Maybe whatever this entity is somehow gets lost because it's nearly the same size as the particle when we go in the other direction. Right? This entity only becomes distinctive when rho prime is big, so that there's a big difference in size. Is perhaps another way to say it. So
You're in the geometric.
that's an excellent question now.
Could it have to do, I mean, we know when we do this, when we get this hot spot, we're in the extinction paradox, right? So, and we got one extinction from that -1, and whatever's left is giving us another extinction. Can we isolate that and say,
Okay, so next time I'm going to show you that the hump disappears when we have significant absorption, but the rest remains. So if I turn on the imaginary part, this stays, this stays, this stays, and then it just shoots right across here, the hump goes away. And then I'm even going to show you that about half of all the scattered light is right here, and the other half is right here. And you might know there's an extinction paradox that says that the scattering for a very large object is twice the geometric scattering. Are you aware of that? Yeah. Here's a pi r squared. Here's a pi r squared for a total of 2 pi r squared, extinction paradox. So that builds in the mystery as to, or at least helps us understand. What I'm also going to show you next time is that significant absorption means that light only makes it in to the first part of the particle. And so this then disappears, whatever that is. See? So we have these little hints. And you guys are welcome to tell me the answer, because I don't know the answer.
So also all this Q-space stuff works really well when it's just wave phenomenon, right? The X-ray guys have done this for years and they find the structure. Has this been applied to other wave phenomena? Like I have an earthquake and I have a bunch of seismic detectors at different places and I can get angles and stuff like that.
What a wonderful idea. I don't know. Before I do earthquakes, I'd probably screw around with acoustics
Yeah.
and try to figure that out. But let's remember the X-ray boys didn't have humps and didn't have 2D diffraction regimes because they never had a significant refractive index.
Right, and other wave phenomena, you don't have all that much of it.
Yeah, but in sound, X-rays are in many ways sound, right? Of course, I said that wrong. Earthquakes are sound waves, but they're both shear waves and longitudinal waves. Certainly there are different bulk moduli and dampings and things like that. There are analogies to refractive index and absorption for sound. And so I think you're right. If we had a spherical particle and hit it with a sound wave, and then if there's some effective refractive index for that sound wave, all this phenomenon should unfold. I agree. I saw some article on some clever sound experiment where people were doing weird things with sound, and I wondered if I could do that to light, so working the other way.